Hello guys, my name is Kailash. Today we are going to discuss deterministic finite automata. Introduction to finite automata. Definition of automata. Automata are mathematical models used to study and simulate computational processes. Role in computer science. Finite automata play a significant role in understanding the behavior of computer programs and algorithms. Key concepts. Finite automata are comprised of states, transitions, and input, providing a framework for understanding system behaviors. What is deterministic finite automata? It have three types like deterministic characteristics, deterministic behavior, advantages of determinism. DFS have a unique transition from one state on a particular input symbol, ensuring unambiguous behavior. DFS always move to unique next state for a specific input, making them predictable and well defined. Being deterministic simplifies the implementations and analysis of automata, facilitating efficient processing. Comparison with non-deterministic finite automata. Non-deterministic behavior. NFS may have multiple possible transitions for a given input, requiring more complex evaluation. Ambiguity in a NFS. NFS can have non-unique transitions leading to less predictable behavior as compared to DFS. Practical implementation. DFS are often easier to design and analyze, while NFS provide a greater expressiveness in representing certain languages. Components of DFA. States. The states represent the various configuration or conditions in which system or a process can exist. Alphabet. The alphabet is a set of symbols from which the input strings are derived and on which the automation operates. Transition function. The transition function determines the next state of the automata based on current state and input symbol. Transition function. Function definition. The transition function describes how the automation moves from one state to another upon receiving input. Deterministic transitions. For each state and input symbol, the transition function leads to exactly one next state in DFS. Handling invalid inputs. The transition function must be defined for all possible combinations of states and input symbols, ensuring well-defined behavior. Accepting states. Definition, role in recognition, multiple accepting states. Definition. An accepting state is a designated state in which the automation signals are successful recognition of an input string. Role in recognition. Accepting states determine whether a string is accepted or rejected by the automation, indicating the language recognized by automation. Multiple accepting states. DFS can have one or more accepting states, leading to different recognition criteria for input strings. DFA representation. You can see a state diagram, transition table. State diagram visually represent the state transitions and accepting state of DFS, hiding in understanding and analysis. Transition table. Transition table provide a clear and concise representation of transition function, facilitating implementation and evaluation. And let's see mathematical models. DFS can also be represented using mathematical models such as transition, matrices, enhancing formula analysis and manipulation. DFS is a mathematical model that consists of a set of states, a set of input symbol, transition function, start state and set of final states. The input symbol are fed into the DFA one at a time, and DFA move from one state to another based on the input symbol and the transition function. Example of DFA. Problem statement, state transition, recognition language. Let's see problem statement. An example problem requiring string recognition can be used to illustrate the function of DFA. State transition. A step-by-step demonstration of state transition based on input symbols showcases the behavior of DFA. Recognition language. The example of highlights of role of accepting state in determining the languages recognized by DFA. Deterministic finite automata operation. String recognition. DFS are used to recognize strings that belong to a specific language, enabling pattern matching and validation. Language operation. DFS can be combined or manipulated to perform operations such as union, intersection, and complement of languages. Language acceptance. Understanding DFA operation is a crucial for developing algorithm for language acceptance and processing. Application of DFA. Lexical analysis, network protocol, digital circuit design. Lexical analysis. DFS are widely used in compilers and parsing tools for lexical analysis for tokens and identifying patterns in source code. Network protocols. DFS play a crucial role in protocol validation and packet inspection to ensure efficient and secure data communication. Digital circuit design. Automata theory contributes to the design and analysis of digital circuits, enhancing the development of electronic systems. Limitations of DFA. Non-context free languages, memory and storage, and computational complexity. Challenge and future development. Complex language recognition, hardware implementation, and quantum computing. Conclusion. Understanding DFA and future perspective. Appreciating the principles and operations of DFS is crucial for various fields, including computer science and engineering. Future perspective. Continued research and innovation in automata theory hold the potential to overcome current limitations of DFS. Educational significance. DFS serve as a foundational concepts in educational programs, fostering computational thinking and problem solving. Thank you.